We present a novel method to manipulate motions in videos by modifying the local phase over time in different spatial scales and orientations. Our proposed approach allows us to reveal imperceptible phenomena not previously visualized in clarity and detail. For example, man-made structures like the crane in this video are designed to sway in the wind. Amplifying the changes in this video reveals the swaying of the crane's mast and the undulation of its hook. When a person fixates at a point, the human eye also makes subtle motions. These motions, due to involuntary head or eye movements, such as microsaccades, are amplified in this sequence. They may have medical applications, as the frequency of eye movement can have clinically useful data. For an input video, we perform the following processing. We use a complex steerable pyramid to decompose each frame and separate the amplitude and phase of each band. We then temporally filter the phases at each location, orientation, and scale. Optionally, we apply an amplitude-weighted multi-scale spatial smoothing to increase the phase SNR. We amplify or attenuate the process phases and reconstruct the video. The result is a motion-magnified sequence. We demonstrate our method on a 1D synthetic sequence. The new phase-based method, in green, is able to magnify objects further than the linear method of Wu et al., in red. We discussed the bound in the paper. The phase-based method also has excellent noise characteristics, as shown here on Gaussian IID noise. The linear method amplifies noise with signal. In contrast, the phase-based method translates rather than amplifies noise. Now we compare the phase-based results with linear motion magnification by Wu et al. To illustrate the effect of using phase instead of pixel values, we do not apply spatial smoothing to the phases in these sequences. On all of the videos we have tested, the phase-based method has less noise and fewer artifacts. We can further improve our result by spatially smoothing the phases. Although it was not suggested by Wu et al., we also compare results when applying video denoising both before and after linear motion magnification. In this case, we apply state-of-the-art denoising algorithms after linear magnification. The denoising algorithms cannot do much with the medium frequency noise in the linear result, while the phase-based result has significantly less noise. Video denoising is also computationally expensive, taking about 10 times longer than the phase-based method. Applying video denoising prior to amplification can help in some cases, but it can also kill the motion signal as VBM3D does on the guitar sequence. The representation we use determines the maximum magnification possible. With an octave bandwidth pyramid, the magnification of the impulse is limited because it is attenuated by its Gaussian window. We can deal with this artifact by using a half-octave pyramid. This results in a wider spatial support for the filter. We can widen it further with a quarter-octave pyramid. The artifacts that we see in the synthetic example also occur in 2D natural sequences, and are reduced as we increase the number of filters. In this side-by-side comparison, there are fewer artifacts when the video is processed using the half and quarter-octave pyramid representations. Ordinary videos hide subtle changes at different temporal frequencies. In this video, the low frequencies contain the swaying of the trunk. At mid-range frequencies, we see the motions of the branches. At high frequencies, the motion of the leaves is most visible. A user can use an interface we created to sweep through the temporal frequencies of a video. For this video, the motions of the shoulder and chest are most visible at the lower frequencies. As the frequency is increased, the motions of the head become visible, and finally at the highest frequencies, only the motion of the eye is visible. Our phase-based formulation also lends itself naturally to the attenuation of motions in videos. In this sequence, we show that we can amplify colors without amplifying motion by first attenuating the phases and then applying Wu et al.'s color amplification. On the left, atmospheric turbulence manifests itself as low to mid-frequency jitters. On the right, we use our method to remove the turbulence. Motion magnification can cause artifacts in regions of large motion such as those around the jumping boy. By automatically disabling the amplification for regions in which the phase change exceeds our bound, we can remove these artifacts as on the right. The subtle motions of the platform shaking are still amplified. At the miniature scales of motion we are after, one might ask, would our magnified motion resemble the motions in the scene had they actually been larger? To answer this question, we conduct controlled experiments. In the first experiment, we induce small motions in a metal structure using a hammer and record the motion with an accelerometer. We also record the structure with a video camera. We amplify a sequence with an oscillatory motion of 0.1 pixels by 50 times. The resulting video is similar to a sequence with an oscillatory motion of 5 pixels, which was obtained from a harder hammer hit. In a second experiment, we mount a sheet of rubber on a PVC pipe to create a tense membrane. We send a waveform of our choosing through a loudspeaker to vibrate the air, which in turn vibrates the membrane. We found that the motions of the membrane magnified 10 times by our method look similar to a sequence where the amplitude of the waveform is 10 times larger. We were also able to separate and amplify different modes of the membrane when we play a composite waveform of 76 Hz and 110 Hz. The modes have different spatial patterns. Thank you for your attention.